Got it. Wonderful. Well, good morning, everyone. My name's Matt Farrell. I'm here with my colleague, Renuka Dhandapani. You'll be hearing from her shortly. So Renuka and I work in the Textile Chemistry Research Department here in Cotton Incorporated in the Product Development and the Implementation Division. We're always excited to be with you and share the research that we're doing. I had the opportunity in January to share the work that we're doing with cotton textile waste and turning that into glucose. And so today, we want to sort of pull back the curtains. I don't know how many of you are really familiar with the work that we do in the PDI division here in funding outside research projects. So this allows us an avenue to do some really creative, excuse me, and exciting things. And we'd like to share some of that with you this morning. So when we get into it, every year we get a separate budget line item to allow us to carry out external research. And so if you've ever been to Cotton Incorporated, if you've looked around, we have tremendous facilities, tremendous capabilities, but sometimes there's things that we want to do or research that we simply don't have the capability or the expertise to do. So on the next slide, we'll give some of those examples. But when we carry out this research, we work with people everywhere, all over the world, all types of research organizations. We work with the USDA. We work with universities, whether they're here or whether those are abroad. And so every year, we put out pre-proposal or a request for proposal. If you've ever heard the saying, there's no such thing as a dumb question, I'm not sure that that really applies to ideas, but I guess I can put it a little bit better. There's things that align better with what we're looking to research. And so at some point in the past, we got smart and decided to only ask for a pre-proposal. So what that means is every year we put out a call for proposals. And so instead of those researchers taking the time to develop a full 20-page document and us here at Cotton Incorporated having to review every one of those, we asked just for a simple one-page document. Let us know what your idea is. This allows us to do a very simple look to see what's out there, to see what type of responses that we've obtained this year. So this year we were just short of almost 70 pre-proposals, and that's a lot. We were able to weed those down and request about 18 full proposals that we'll be reviewing very shortly to finalize and select final projects for funding. And so every year, we're able to fund a handful of these projects, maybe 5, 7 to 10 of these that are directly funded outside of our typical research activities in-house. So to give you some examples of some of the types of things, that we're working on, it's real important to show for us how cotton compares to synthetics, especially in terms of biodegradation. So those are very specific conditions and requirements to carry out that research. So we work with outside universities to carry that out and show how well cotton biodegrades across various environments compared to synthetics. Back in January, you heard me talk about something very special for me, which is cotton to sugar. We've also worked with outside universities such as NC State to carry out research in that area. Another thing that's very important for us is to show how cotton compares to synthetics in different situations. So think of, say, synthetic garment that you had. It had that permastink to it. We were able to show that cotton does not hang on to odors like some of these synthetic garments, a positive. Also able to show that cotton is much more comfortable, say, to sleep on a cotton sheet compared to a synthetic sheet. Again, we go outside to find researchers that have those capabilities to do that. And of course, an area that's also important for me is we've done a lot of work in trying to show and improve the sustainable dyeing of cotton. How do we utilize less dye stuffs, energies, and inputs? So every year when we develop this RFP, we have a small committee of us and we put out this RFP. I really want to stress that we put a lot of time into really owning in on new initiatives, new ideas, and we stress to the researchers that our focus is on applied research. So what that means is there's an overlay of academic and I would say industrial and actually getting an idea out. So we want to be right in the middle there where we identify things that if they work and they're successful, they're easy to translate over from the laboratory and actually get those ideas out into the public domain. And so at this point, I just really want to set an idea into your mind. I want you to think back maybe to when you were in grade school. I know it's hard to imagine, but yours truly was a knucklehead. Now I know why my grandmother always said she wanted to see, me have kids, but luckily my kids got all my wife's good qualities. But I have a very fond memory of childhood, and we had an invention contest. I went in the kitchen, I grabbed milk and vinegar, all kinds of nasty things, and mixed it together. I called it Girl Off. It must have worked. My mom didn't want it at home. My teacher didn't want it in the class. But going through all of that, I got this little plaque. And at the time, it didn't mean that much to me. But the older I've got, I think this really, really captures what we're trying to do here at Cotton Incorporated. And I hope as we present what we're working on, this resonates with you. And it says that some people see things as they are and ask why. I dream of things that never were and ask why not. Those are the questions that we're asking here at Cotton. Why can't cotton be used in these new areas? Why can't it be utilized in different ways? And so that's really what I want you to think about as we go through the rest of these slides. So you're going to hear a lot about cottonseed oil this morning. And I'm going to present some very technical things and technical terms, and it's heavy at times, but I think it's really important to expose you to the level of research that we're doing and what we're trying to do. And of course, if there's any hard questions, make sure to ask Renuka at the end. So when we really get down into it and why we care about it, especially, we're chemists from a chemicals perspective. Cottonseed oil is a very fascinating product to us. So it's a combination of all types of various fatty acids and triglycerides. And I know these are words you've probably heard before, especially if you go to the doctor, they're checking. If you're like me, you like to eat a lot of fried things. They want to make sure you're not creeping up too high on those triglycerides. So cottonseed oil, it has a very high smoke point from its qualities. And so that makes it really good for things such as frying. And that's why it's in a lot of fried foods. But it's important to note that cottonseed oil, you've probably heard of saturated, unsaturated, transaturated fats. If you've ever looked at the back of a material or ingredients in what you're eating, you'll see those listed. And it's important to note that cottonseed oil is considered unsaturated because it has a lot of linoleic acid in it. And this is an unsaturated fat. So there's a lot of triglycerides that are in cottonseed oil. I just really want to call your attention to one specific one, and we're going to look at it here in a second. And that's a triglyceride composed of palmitic acid and linoleic acid. And so that's really interesting to chemists because we're weird. And I just want you to look at this bottom picture. So hopefully you'll see that there's 3 chains on this molecule. That's why we call it a triglyceride, since there's 3 of them. The only thing I want you to take away from this picture is in that bottom picture and in that blue circle. That's what we call a double bond. And so that's what we refer to as unsaturation. And that's what makes chemists really happy, because cottonseed oil has a lot of this that we can potentially play with and do something with. So one day I was sitting around thinking, what if it would be possible for us to finish cotton with cotton? So what I mean by that, what if we could take use of all that potential reactivity in cottonseed oil? What if we could change that into something else and actually finish cotton with that derivative? And so that would have the potential to replace things that are purely petroleum derived, purely synthetically made. And so through this avenue that we're talking about with outside research, we were able to work with NC State University for several years to develop a process to epoxidize cottonseed oil. And that's hopefully will become clearer in the next couple of slides. So they were able to make all types of different softeners, use this epoxidized version as is to apply to cotton fabrics. And so what this allowed them to do is they had enough background information and research that they were able to apply for a NEFA grant and receive funding to continue this for 3 years. So we're really excited to see this work keep progressing and what's actually possible with cottonseed oil and finishing cotton. So I know it's a chemical reaction here. And again, I just want to call your attention here. This is that triglyceride. There's that double bond. And I just want you to look at the bottom of this picture on the left. What you're going to see is a triangle that has an O in it. So this is what we call epoxidized cottonseed oil. And if you think of something as an analogy, think of something like a bear trap. You know, it's happy until you prime it and spring it open. It's ready to pop. That's the same situation with this epoxidized version of cottonseed oil. So we like it because in this form, we can take it and do all types of different reactions and derivatives with it. I'll call your attention to this picture on the right. You can see the lab set up to actually do all this epoxidation. And what's really interesting on the far right side of the screen is the time. So you can see in the top this cottonseed oil starting out as is. You see the color as it starts to react, it changes and gets darker. And in the end, it's almost a colorless version when it's epoxidized. So it's really interesting to see visually what we know is going on chemically. So part of the research that we do in having these ideas, it's great that you can make, something out of cottonseed oil, but what would be even greater is if you can prove that it has a measurable effect. So just on the left here, you can see and imagine working in a lab with small samples. You can see a little flow diagram of how they've treated cotton fabrics in a solvent. This is easier to do initially instead of water. But what's really interesting is the picture here on the right, a water contact angle. This is a test that we routinely carry out. So what happens is we have a water dropper, a camera, and we have the fabric. So a drop of water is placed on that fabric, and the picture is taken to measure the angle. So you can see at the top there with untreated fabric, the water completely goes in. There's no angle. On the bottom, you can see that this type of application with this epoxidized cottonseed oil is highly repellent. It has a high water contact angle, clearly showing that this stuff is reacted and is doing a finish, a water repellent on cotton. So along those same lines, another technique that we look at when we're analyzing these types of treatments is scanning electron microscopy. So we treat fabrics with gold, and that just helps us image them. What I will call your attention to is the far left top is a control, untreated cotton fabric. You can clearly see the fibers. You can see the weave pattern. On the far right is an extreme application. And so this would mean that there was a lot of this oil put on. What's interesting with epoxidized cottonseed oil and what you can see is not only does it react with the fiber, but it can also react with itself, creating a coating. And that's what you see here. So in August of this year, this research was presented by the researchers at an American Chemical Society conference. And so there was great publicity, and there was a press release generated by the ACS. And this is exactly what we're trying to do with this research. You can see, I just grabbed a couple of pictures of where this was picked up around the world. We push the researchers to publish. We don't want to keep that at our chest. We want people to see what cotton is doing, what cotton can do. And this is exactly the type of outcome that we look for when we're funding these types of projects. So I had mentioned that this work was trying to prove the application of these epoxidized cottonseed oils in solvent. Anybody familiar with textile-based applications know that we work in an aqueous application environment. And so one of the things that Cotton Incorporated is really good at is we're interfacing with industry. We're interfacing with these academics who have these great ideas and are able to do these great things. But how do we bring that all together? So you can see here in this top middle image, there's a picture of this epoxidized cottonseed oil. It's an oil. You can't just drop that in water and pat it on. You can see a laboratory pattern here on the right. So our friends at HiQ, they developed an emulsion. So think about just putting some soap in with this epoxidized cottonseed oil, mixing it up, and making basically an emulsion that we can then put into water and apply. And this is where this research will continue to push and prove that we can do this in an aqueous-based environment. So one more example I want to give you, still around cottonseed oil is about non-isocyanate polyurethanes. And so I guarantee you it's some part of your life that you have utilized a polyurethane, whether knowingly or unknowingly. They are in everything from coatings, glues, sealants, foams, fibers like Lycra. My wife and I took the kids to the fair yesterday. I got sunburned and a stomach ache. I needed my stretchy pants this morning, so I'm glad that there's somebody making those. However, these types of polymers come with some issues, and so they're made from a lot of non-renewable resources. And I can speak personally about the toxicity of isocyanate. In a past life, I had to take a test even to get a sample of this stuff because they're so dangerous. One of the researchers that we funded last year, he had a really good idea, I thought. And remember those double bonds that we talked about and looking for those triangles? If you just quickly look at the picture on the right here, these researchers are able to utilize an enzyme to make that epoxidized form in that triangle. That's what those little beads look like in that small square image. So it's fascinating that they're able to do this from a naturally derived enzyme without having to do all of this chemistry to get to that form. Additionally, with this research, instead of using isocyanate, which we mentioned are problematic, they're able to incorporate carbon dioxide from the air and make a reactive form to make a urethane. So this is just from a chemist perspective, this is very fascinating to see and know that cottonseed oil can be used in this pathway in this potential type of opportunity. So just very quickly to show you what that looks like, here's this non-isocyanate polyurethane. So you can see here on the far left, this is a much simpler setup using those enzymatic little beads to epoxidize cottonseed oil. In the middle here, we see how we're introducing that CO2 to get that version that will react to make a urethane. Again, as we mentioned before, it's great if you can make these compounds, but what do you do with them? Do they do anything for cotton? Here you see a curing oven. Here you see samples that were treated and cured, and similarly to what we saw before, that water contact angle clearly demonstrates that these types of urethanes are highly hydrophobic and repel water. These SEM images, you can see how there's not a lot of surface coating, so they're very powerful polymers that we're putting on. And on that far right, you can see that water bead just sitting there because it's not going in as compared to the untreated fabric on the top. So before I turn it over to Renuka, just to sort of summarize where we're at with what I presented, hopefully you have a little better idea, if you didn't before, about the process that we utilize here in the Product Development and Implementation Division to carry out funded outside research. And so we develop and distribute RFP. We collect pre-proposals. We narrow those down to solicit full proposals and make final selections of those. Some of the specifics for what I was presenting for cottonseed oil, I hope that you see that it's a powerful potential building block for making chemical and replacing things like synthetic or problematic chemistries. It's easily epoxidized, and we can use that as is or further modify it. And so with that, I'm going to turn it over to Renuka.
Hello, this is Renuka Dhandapani, and continuing with our presentation today, I really wanted to look at the next topic that I'm going to talk about. This has to do with the research we did with Deakin University in Australia. So in this case, we were trying to upcycle the byproducts that come from cotton ginning trash. And we know that there were two different types of byproducts we were looking at: the cotton gin trash, which contained more of plant waste, and the cotton gin modes, which contained more of the fiber. The main goal of this process was to convert the big particles or big chunks of material into fine talcum-sized powder material. So basically, we took the gin trash, took a rotary cutting mill, chopped it down to coarse powder, which was further grounded using metal balls into a fine slurry, which was then spray dried, and we were able to get a 20 micron size powder. So this was our starting material. What we did with that was something like making a smoothie, where you're taking two different polymers, blending it together to get a consistent material. So in our case, we took the cotton gin crash powder and blended it or compounded it with a biodegradable polymer. And we used a twin screw extruder where both the polymers we added with two different entry points. And based on how much consistency you needed in the final, they were either increased in speed or decreased in speed. They were blended together and extruded as a filament, which was cooled down and then chopped into pellets. Using these pellets, you can take it down to either making a composite film, or you can do it a 3D printing, or you can use it in injection molding, anything. But this would be our starting material to work with. And what we did was make it into pellets and make a film from it, bio-based film. And first of all, I wanted to bring your attention to the pellets in the first container, where you see it's non-uniform. The challenge we had over there was when we were mixing two different polymers, they were not working well together. So after a couple of trials and errors, we found that we needed to add a third component, which was a plasticizer, which acts as a lubricant, which brings two different polymers together, makes them work together well, and gives you a good product. And that's where we were able to do that. And we got pellets which were more consistent in shape and size. And this was hot molded into flat films. And using these films, the next thing we wanted to do is make sure we checked the properties of the developed films. So we compared it against a Ziploc bag. And the developed films we realized was more stiffer and less flexible than a Ziploc bag. So basically, with the property being this, we thought the films would be more ideal for something where you needed more stability with the more rigid format and less stretchable material, sort of. And we also did was to do the transmission spectra reading on the films. And we realized that the newly developed films was able to completely block UV light. So which is really advantage when you consider a film that can block UV light, has more rigidity, and can have transparency. These films would be more ideal for application where you have food packaging, or say cosmetics or pharmaceutical packaging, where you needed products to be protected from photodegradation. This film would be really good. And we did a live application, or rather real-time application. We used the film as mulch cover. We wanted to see if this would be something that can be considered for mulch cover. So in our case, what we did was we took the films and cut it into pieces, and we covered it on top of the soil and had the edges tucked into the soil. So basically, we did a 3-month study to see how the films changed, or how it worked in a real life experience environment. So when we did that, we noticed that over time, as we tracked, the part of the film that was tucked into the soil started to biodegrade. And the top of the film that was exposed to the sun actually changed color. But when we did the UV blocking measurement again, it still worked as the initial or original film. So that was not a problem there. And we also did a commercial film to compare against. The commercial film didn't show much of a change. So this was really good for us to know, because we realized that the film that was developed and used for mulch is actually good for UV blocking. Hence, it prevents any weed from growing around the crop. And at the end of the season, you can actually just bury the film in the soil, and it's going to break down and not leave any lingering parts in the soil, because that is one of the challenge we have right now with the mulch. And this actually helps because it breaks down completely in the soil. Then going to the next project that we did with North Dakota State. And this is something like what Matt was talking about, using the functionalized cottonseed oil. What we wanted to do is try to use it in making a coating or composite application. So we wanted to develop a bioresin from it. And we did it in a 2-step process. The bioresin was developed from cottonseed oil. And we also compared it with a reference material. We bought a soybean oil from commercial soybean oil. We made a product of it, which followed the same process, made the bioresin. We compared the properties of the two materials. And we realized that the bioresin that was made from cottonseed oil had real good flexibility. So this would be really ideal when you're doing on a flexible surface such as paper and textile. The cottonseed oil bioresin would be a really good example to use over there. And the next thing I wanted to talk about with cottonseed oil, we have been doing multiple things with cottonseed oil here. So with cottonseed oil was to develop low density foam. So this is more like baking cake. Like you just think you're mixing a functionalized cottonseed oil, you're mixing your cross-linker, foaming agent, and accelerator, you mix it well, pour it into silicone molds, and you're baking it at 160 degrees C for 30 minutes. The main goal or idea of this project was to avoid using isocyanates, which is mainly used in polyurethane foams, but it also has a lot of challenges, environmental and health concerns. So we wanted to avoid that. And we therefore looked at another foaming agent called azodicarbonamide, ADA for short, which according to FDA is safe. And usually this compound is used in baking goods. So this is something that's really safe product. We wanted to use that. And the good example, if I can bring your attention to the image on the screen here, when you just use the foaming agent, it's still not enough, because when you use the foaming agent and you bake your product, you get a flat foam. You don't get any fluffiness in it. So you need to add an accelerator. In our case, it's zinc oxide, because zinc oxide, what it does is at 160 degrees C, it helps to break down the foaming agent pretty quickly and generate gas. And that's what, if you look at the cross-section view, you can see a lot of bubbles. Those are your gas logged into the structure and gives it a fluffiness to the product. And not only that, when we looked at the foam, we realized that the foam had memory retention to it. So whenever you press and hold, release it, it bounces back to its original shape. And you can cut it into different sizes and shapes. So it does have a really good advantages. Because of this, I would say the foam is really ideal for cushioning purposes in your furniture, shoes, your bedding or packaging application. And what we wanted to do is, using all these different versions of cottonseed oil, we wanted to combine them together and make it into vegan leather. So we use the base skin layer, which is your bioresin, and the mid layer as your foam, and the bottom layer was cotton fabric. So if you see the schematics here, we basically use the glue to apply on the top and bottom of the foam. And the top layer was your bioresin and bottom was your cotton fabric. And we sandwiched the whole thing and UV cured it. And we were able to produce vegan leather from it. And if you look at the SEM image here, you can see how all the layers are really compact. Together, there's like the glue really holds on everything together in the structure. Then moving on to the other version that we did with cottonseed meal, which is supposed to be a byproduct from cottonseed oil extraction. We wanted to see if this can be used in making anything advantage or can be made of any value-added product. So we were able to extract protein from cottonseed meal. Basically, by using the one-step process that was developed, we were able to extract 3 different types of proteins from the cottonseed meal. And we really got a high yield, about like 90%, and a high purity of the protein from the cottonseed meal. So at this point, what we did was we went and dissolved the cottonseed meal, and we were able to film cast it and make films from it. Initially, when we made the films, we realized that by using a plasticizer, we ran into some issues here, because the plasticizer over time separated out of the films and the films became brittle. So we had to go back to the figuring out how to make the films without a plasticizer. And when we did this combination, and over time, we were able to get a stable film, which stayed, this one, like when you look at the bar chart, you can see like over 9 months, the tensile properties of the film did change. So it was pretty consistent and it retained its tensile properties and didn't modify or change over time. So these sort of films would be really ideal or helpful for food packaging applications. And to bring a quick conclusion on a couple of ideas that I've been talking so far, is that traditionally we know that cotton plant has been textile focused. That is what the focus has been so far. And we really want to find new markets. We wanted to find opportunities where cotton can be used and you can increase the product value for cotton. So like I did cover a couple of points where we use the cotton gin byproduct to make UV protective biodegradable films. We use cottonseed oil to make bioresins, and also we used it in making low density foams that can also be used in vegan leather. And the protein that was extracted from a byproduct of a byproduct, we were able to use that to make films that had extended shelf stability, and which can be targeted for your food packaging or barrier applications. So with this, I would like to conclude our presentation, and we are open for questions over here for now.